Okay, welcome back. So today we're going to talk about solving systems of equations using what's called Cramer's rule, which makes use of matrices and idea of what's called a determinant. Now, a determinant is simply a way to identify and calculate values based on the matrix itself. So it has to be based on a square matrix to begin with. 2 by 2 determinant, second order determinant, is 2 by 2 matrix, where if we have matrix A here is defined as A, B in the first row, C, D in the second row. The determinant of A, which we will abbreviate as dA, like that, is just going to be the the difference of the diagonal products. So AD is the left diagonal, minus BC the right diagonal. Very straightforward. The 3 by 3 third order determinant is a bit more complicated. There is a rule for that, which we're not going to use really to solve out. In class, we're going to instead use the calculator. So make sure you're referring to the calculator video that shows how we're using this, how using your TI-84, TI-83s to identify your determinants. 2 by 2s, you can still use the calculator for as well. The calculator video will show that just to kind of prove to you that it can work. But for the 3 by 3, we're not going to discuss the diagonal rule that goes into that. It's not that bad. It's essentially creating 3 left diagonals and 3 right diagonals, summing the left, summing the right, and then doing the difference there. It just gets overly complicated in the context of Cramer's rule, as you'll see in a little bit. So for our 2 by 2, we're doing our left diagonal, which would be negative 5 times 8, which is negative 40. Our right diagonal, which is 4 times negative 3, which is negative 12. And it's always left minus right. So it's negative 40 minus negative 12, which is going to be a negative 28. So that's the determinant of that particular 2 by 2 matrix. So for the 3 by 3, you'll want to make sure you can practice using your calculator for this one right here. You should be finding that this determinant is going to come out to be a negative 72. So make sure you've watched that video, you reviewed it, and you're practicing the material right now to get that particular determinant value. Now, when it comes to solving these systems with Cramer's rule, what's going to happen is you're going to create one more matrix than you have variables. I mean, if we have a 2 by 2 system, 2 variables, 2 equations, you need 3 matrices. If it's a 3 by 3 system that has 3 variables, 3 equations, you'll need 4 matrices. And we're going to find the determinants for each of these matrices and use that to solve the equation. So if we have this generic 2 by 2, ax plus by equals m, fx plus gy equals p, you're going to find that matrix C, our coefficient matrix, is just simply the coefficients of the equation, a, b, f, g. Whereas matrix X and Y is going to replace the column of the coefficients matching that variable with the solution at the end of the equation. So notice the first column for X was the X coefficients. It gets replaced by M and P. Whereas the second column for Y was the Y coefficients. They get replaced by, again, M and P. And then we use these determinants to identify the solution. So the value of X, the variable X, is the determinant of X over the determinant of C. The value of y is the determinant of y divided by the determinant of c. So if we look at this equation right here, we're going to set up our 3 matrices. Our C matrix would be 4, 2, negative 3, 3. Nothing changes from there. Our X matrix, we would replace the X column, 4 and 2, with the negative 1 and 13. We leave the Y column alone. And again, you're just replacing the column, so you're not moving any of the other columns around. So the Y column is always second, X column is always first. It's just that when it gets replaced, it just has new numbers appearing there. So for the Y matrix, X column is left alone, but now we replace the Y column, negative 1 and 13. So we go through and find our 3 determinants. Determinant of C would be our 4 times 3 minus 2 times negative 3. That gets us a positive 18. Our determinant of X would be negative 1 times 3 minus 13 times negative 3. That's a positive 36. And our determinant of Y would be 4 times 13 minus 2 times negative 1. And that would be a positive 54. So our value of X is going to be 36 over 18, which is 2. Our value of Y is 54 over 18, which is 3. So our final answer, since it's always an intersection of 2 equations, is the coordinate point 2, 3. For all our problems, you'll find that they're going to be nice values, nice integer values, though obviously they don't have to be for future classes, future courses. But everything we're going to work on will be nice integer values. So that's going to be a little red flag for you. If you get a decimal answer, one of your determinants is wrong. Now, which one it is depends on what's happening with the decimal. Like if x is a decimal but y is okay, it probably is your x matrix is probably wrong, set up wrong somewhere, or that determinant is probably wrong. If they're both decimals, it's probably the coefficient one then, because you're dividing by the same number each time. That's what's probably messing it up. So just look back at your construction of the matrices, look back at your calculations, and see where you could have gotten wrong. All right, so let's take a look at another 2 by 2. So here our coefficient matrix is going to be -5, 10, and then 2, -4. Our x matrix, we will replace the x column with 10 and 20, leave the y column 2 and -4 alone. And then our y matrix, we replace the y column with our 10 and 20, we leave the x column alone. So the determinant of matrix C, or coefficient, would be -5 times -4 minus 2 times 10, which is 0. And when the coefficient matrix determinant is 0, we now have our special case, because the solutions are always divided by the coefficient determinant. And if that's 0, we can't divide by 0. Now, whether or not it's no solution or infinite solutions is fully dependent upon what the next determinants are going to be. So the determinant of x is 10 times -4 minus 2 times 20, which is -80. And the determinant of y is -5 times 20 minus 10 times 10, which is -200. So if all the other matrices are non-zero values, then this is no solution. If all the determinants are 0, then it's infinite solutions. Now keep in mind, this only applies when the determinant of C is 0. So the determinant of C is like 12, and the determinant of x is 0. That just means the value of x is 0. Because again, it's all about we're dividing by the determinant of C. If that's 0, we have a special case. You're not going to have a scenario where like determinant of C is 0, determinant of x is a non-zero number, but the determinant of y is also 0. That can't happen. So either it's determinant of C is 0 and nothing else is 0, or they're all 0. All right, so that's our 2 by 2s. The 3 by 3s, it's going to be the same kind of process. You'll just find that it's because there's a third variable, there's now going to be a fourth matrix involving with z. So here we have our coefficient matrix. So our x column would be 0 because there's no x in the first equation, -3 and 2. And our y column is 5, 2, and 5. And z column is 2, 9, and -1. And then our x matrix, we replace the x column with the 18, 8, and 15. And we leave everything else alone. Our y matrix, we would now leave the x column alone. We replace the y column with the 18, 8, and 15. And again, the z column is still left to where it is. And then find out the z matrix, now we leave the x and y columns alone. So 0, -3, 2, and then 5, 2, and 5. But now we replace the z column with the 18, 8, and 15. As you can see, we have 4 3 by 3 matrices. This is the perfect reason why we are not worrying about 3 by 3 determinants by hand. They are rather tedious, ripe for a lot of simple calculation errors. Now you're doing this 4 times to solve one question. It can get a little messy. So your determinant of C, when you're using your calculator, you should be finding to be 37. Your determinant for x would be -111. Determinant for y is 148, and the determinant of z is a -37. So x is -111 divided by 37, which is -3. Y is 148 divided by 37, which is 4. And then z is -37 divided by +37, which is -1. So -3, 4, -1 is the solution of this 3 by 3 matrix. All right. Let's do one more. Let's just kind of show you what the infinite solution situation looks like. Here, when we get all our determinants, will end up being 0. So our coefficient matrix, x column is 1, 3, and 3. Y is -3, -9, -9. Z is -4, -9, and then 0 because there's no z at the end. So the x matrix, we replace the x column with the 14, 27, and -18. We leave everything else alone. Our y matrix, we now replace the y column, the middle column, with the 14, 27, and negative 18, and everything else is again left alone. And then finally, the z matrix, we leave the x and y columns alone, and replace the z column with our with our 14, 27, and negative 18. And you'll find, again, when you're using your calculator, each of these determinants to come out to be a 0. And again, make sure you are comfortable with this calculator process there, because again, we're not doing it by hand, and you have no way to intuitively know whether or not this is going to be a 0 or not just by looking at it. So you need to make sure you're careful with the calculator you use. You're careful typing in the numbers. You're essentially typing in 4 different matrices here. There's 36 numbers you're typing into this thing. You got to make sure you're careful as you work this out. So again, this would be infinite solutions because all your determinants are 0. All right, so that's our Cramer's rule for solving a system of equations. Obviously not the most useful really with the 2x2. It's typically your substitution elimination strategies, even if the answers are decimals, will work out a little bit quicker. But both these rules, the rule is really useful for when you're using a computer to calculate this stuff rather than trying to do it by hand, because it's easy to type in a computer code for matrices to solve something out rather than trying to tell it to be able to do a substitution elimination process instead. All right, so we have one more video for solving equations using matrices. We'll talk about the inverse matrix in that one, and we'll move on to some other non-matrices ideas. So I'll see you guys next time.